All right, so our next topic is going to be start with our derivative shortcuts. The first thing we get is that there are three shortcuts that you need to know. Remember, these are slopes of lines tangent to the graph. So if you have a function like f of x equals some constant equals c, remember that if it equals a constant, that means it's going to be a horizontal line. What's the slope of a horizontal line? F prime of x equals 0. Because the slope of a horizontal line is 0. So therefore, if you're having a constant like the derivative of 100, that's going to be just 0, that derivative. If you have a line, if you have y equals or f of x equals mx plus b, recall from algebra 1 that the slope of that line, f prime of x, is simply the slope m. And finally, the $1,000,000 rule that we love to use is that if f of x this is called the power rule. So if you have f of x equals some constant times x to the nth power, to find the derivative, what I'm going to do is I'm going to bring the n down, I'm going to multiply it by c, and I'm going to reduce the power by 1. So f prime of x is equal to n times c times x to the n minus 1 power. And remember, that's going to be called our power rule. So let's say that we had something like we did in our previous video where I had f of x equals x squared. Using our power rule, f prime of x is equal to 2x. If I had, remember, that one was not too hard to work out, but if I had f of x equals the square root of x, we want to write that as a fractional exponent, which is x to the 1/2. We're going to bring the 1/2 down, and we're going to reduce the power by 1. So it's 1/2 x to the negative 1/2. And recall that that negative 1/2 only goes with the x, so I can rewrite that as f prime of x equals 1 over 2 times x to the 1/2, or the square root of x. And that's what you got when we worked it out by hand, but boy, that's a lot easier. Same thing with fractional exponents. If you have something like f of x equals 1 over x, write that as x to the negative 1 power. And then when I take the derivative, f prime of x, I'm going to bring that negative 1 down. So it's negative x to the negative 2, which I write as negative 1 over x squared. You're going to use that power rule over and over, and it's really built into many, 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 many of the other rules that we have throughout the rest of the course. So you just have to know that one by heart, and it's a pretty easy one. Another concept that we get into here is differentiability, and the book goes through and explains it really technically. I'm going to give you the common sense version of it. A function is differentiable when it's turning nice and slow, it's not doing anything crazy. The two things you want to look for are, when is the function going to have any breaks? In other words, when there are any points of discontinuity, the derivative doesn't exist. And whenever you have any sharp turning points, the derivative doesn't exist. So let's say that I had something like, hold on, what's going on here? There we go. Something like this, and then I broke, and then I went up here like this. Let's come down and make a sharp turn. So right here, and the break, let's call that point A, and then right here, let's call that point B. And let's say that those are my 2 points that I'm interested in. The derivative would not exist at those 2 points. Any sharp turning points or any discontinuity, the derivative does not exist. And that's why we did continuous functions in at the end of our last unit. And then the other thing that you need to know from this part is some of the derivative notation. And there's lots of different derivative notations, lots of different ways of writing it. So let's say that we have, if we want to find the derivative of something that is y, we can write it as y prime. If it's f of x, we write it as f prime of x. This is the first derivative. If you want to write it in terms of the change of y over the change of x, you'll see dy dx. If I want to indicate to take the derivative of something, I take d dx of f of x. Those all mean first derivative. And then sometimes you'll see some other notations, but those are the most common. If I want to take the second derivative, I can keep doing the same thing. So it's like y double prime or f double prime, or in the second derivative you'll see d2y over dx squared. And we can keep going with that. So third derivative follows the same pattern, and so on and so forth. So, they keep on going. You can look, there's a whole table in our book, I think it's like around page 170, 169, somewhere in there, that have different derivative notations. But those are the most common. If you get to one that you're not sure of, please ask and I'll clarify it for you. But you got to be familiar with all of those. Just another example I wanted to kind of do with you is if you have a polynomial function. Let's say we have y equals 2x to the 1/2 plus 3x squared minus 2 over x. First of all, our fractional exponents and our negative exponents, I want to find the derivative of this. Our fractional exponents and our negative exponents are really helpful for us. So we want to rewrite it with fractional exponents and negative exponents first. Then after we do that, we're going to follow our power rule, and it's a polynomial function, so we can go ahead and take the derivative of each piece individually. So I'm going to write it as y equals 2x to the 1/2 plus 3x squared minus 2x to the negative 1. Now follow power rule for each one. So y prime is, bring the 1/2 down, multiply it by 2, and that's just 1. So I get x to the negative 1/2. This is going to be plus 6x, and this one's going to be plus 2x to the negative 2. Decrease the power by 1, don't increase it. And then ultimately you'll see us put it back into like the square root of x plus 6x plus 2 over x squared. And that's the derivative of that original polynomial. Alright, well, so you get to start working with some shortcuts and some derivatives. Good luck on this first assignment.